In this lecture, we're going to discuss the concept of divisibility. This is essentially our way of understanding the multiplicative structure of the integers. So let's start with the definition. So for two integers, let's call them a and b, we say that a divides b. I'm going to write it like this with this vertical line. But the way you say this in words is a divides b. What does that mean? So other ways to think about this are b is divisible by a. A is a smaller thing, so b is divisible by a. A is a divisor of b. A is a factor of b. Lots of ways to say this. They all mean the same thing. I wrote it in words a bunch of times. What does this mean in mathematical symbols? So we say a divides b if, let's do this very carefully. So if there exists an integer, underline that because that's really important, an integer c such that a times c equals b. Okay, in that order. It's very important that c is an integer. Okay, it's not allowed to be a fraction or anything like that. Let's look at a couple examples immediately just to get some intuition for this. So for example, what if I wrote this? 4 divides 12. Well, that's true. Okay, so this is true. Since 4 times 3 is 12, right? 4 is a factor of 12. 4 is a divisor of 12, etc. Our integer c there would be this 3. What about 4 divides 10? Is that true? So intuitively, probably you're saying no. Yeah, this is false because there's no integer that you can multiply 4 by to get 10. That's how to think about it. You could say, well, what about 2.5? Well, it's not an integer. So that's why I'm really emphasizing integer here. It has to evenly divide. Okay, so that's false. Notice when I write this symbol, like when I write something like 4 divides 12, I'm not going to write an equal sign after that or anything else. This is already a statement on its own. Okay, it's either true or false. Okay, let's just try to think about some more of these. So what if I put it the other order around? 12 divides 4. Is that true or false? This is false, so we have to be careful. It doesn't work if you do it in reverse order. Because there's no integer, so that 12 times that integer is 4. 1/3 is not an integer. 1 divides everything, right? 1 divides n is true for every n. True for every n. What other interesting examples can we do? What about this? Does 5 divide 0? And while we're at it, does 0 divide 5? Okay, how does 0 work here? Okay, so let's think about it this way. So is there an integer c such that 5 times c equals 0? Sure, right? C could be 0. So this one's true, actually. Let's look at the next one. Is there an integer c such that 0 times c equals 5? No, I don't think so, right? Because 0 times anything is going to be 0. So there's no such c. That means this is a false statement. Okay. Here's a really tricky one. What about 0 divides 0? Is that true or false? Well, you might have seen, for example, in a calculus class that like when you have 0/0, that's an indeterminate forms, undefined. But the thing is, like I'm not making any reference to division in this definition, right? I'm just using multiplication. So I think when we see this 0 divides 0, we should take it very literally and just write down a definition. Is there a c such that 0 times c equals this 0 over here? Yes, there is such a c. In fact, there are many, right? C could be anything. But there definitely does exist an integer c. In fact, there exist many. So this is true. So actually, this statement is true. 0 does divide 0, even though 0/0 is undefined. But yeah, it's undefined in this sense. Actually, there are actually infinitely many values that this could take on. Okay, so let's try to discover some properties of this this relation divides. So properties of divides. So first of all, it's reflexive, meaning any number divides itself. Okay. So this is a statement. Okay, that's a true mathematical statement. X divides X, period. Okay, why is that? Well, is there a C such that X times C equals X? Yes, C could be the number 1. Right. This is not symmetric. Okay, when you hear this term reflexive, you're thinking maybe of an equivalence relation. So things are reflexive, symmetric, and transitive. Symmetric would be, if X equals Y, then Y equals X, for example. That doesn't work with this. In fact, this is what I would call some version of anti-symmetry. So anti-symmetric. Essentially, so if I have X divides Y and Y divides X, these can't both be true. Unless, perhaps Y and X are both equal, right? So if, this is how we can say it, if X divides Y and Y divides X, then X and Y are very limited. So then X equals Y. Actually, I should be a little careful here. I think I want to say X equals possibly plus or minus Y. There could be a -1 in there. We didn't talk about negatives, but because we're not really going to use this definition so much with negatives, but they will crop up sometimes. And so, for example, I would say -4 does divide 12 also. And that's because -4 times the integer -3 equals 12. So that also fits our definition. Let's see why this anti-symmetry is true. So what does it mean for X to divide Y? That means there's some C such that X times C equals Y. And C is an integer. What does it mean for Y to divide X? It means Y times, I'm not going to use the same C, I'm going to use a different C, so I'll call that D, equals X. So 2 separate statements. No reason for it to be the same C in both statements. Okay, so can we see from this that X and Y have to be equal or possibly opposite? Well, let's take this Y and then plug in XC for this Y here. So we get XCD equals X. And, well, it looks like that means CD, so that implies CD has to be number 1. Okay, what does that mean? It means that, well, first of all, there are 2 ways that CD could be the number 1. We could have C equals 1 and D equals 1, or C equals -1 and D equals -1. Why can't I have C equals 3 and D equals 1/3? Because C and D are integers. Okay, that's part of our definition here. And in the first case, we get x equals y if we plug in 1 for c. And in the second case, we get x equals negative y. So that's the proof. So they're anti-symmetric. What else about this divides? So it is transitive. What does that mean? It means that if x divides y, and y divides a third number z, what do you think the conclusion is going to be? Then x divides z. Okay, so it's kind of a chain of divisibility here. I will leave this one to you to try to prove. It's good practice. It's not too difficult. What do you want to show? You want to show that there's some number such that x times that number equals z. Assuming these two things. Some integer, excuse me. Okay, what does this suggest, though? So this suggests that divisibility sort of has a structure of a lattice in the integers. So there's a divisibility lattice. So I'll just maybe sketch a little bit of that. So what does this look like? So let's take number 12. Okay, so 12 is divisible by a lot of things, right? Let's put 6 here. And then 6 is divisible by 3 and 2. 12 is also divisible by 4. 4 is divisible by 2. See, so there's sort of a lattice forming here. Or things above, things higher up in the lattice are divisible by things lower down that are connected. And then I guess we have 1 down here. So see, there's all the factors of 12, and 12 divides 4, 4 divides 2, 12 divides, sorry, I'm saying it the wrong way. 2 divides 4, 4 divides 12. So 2 divides 12. That's sort of what the transitive property looks like. This is pretty fun to sketch. They can do one for 8, for example. 8 has 4. 2 is actually a factor of 4, so I'll draw it down here. And 1. So it's a sort of lattice for 8. Let me think of a crazy one. So how about 30? 30 is 2 times 3 times 5, so it's sort of a lot of different prime factors. What's immediately going to be down here below 30? Well, maybe 15 will be over here. And it's also 10. 10 and 15 are not related by divisibility, so I'm not going to draw a red line connecting those. But these both have 5 as a factor. Sorry, the wrong color. These both have 5 as a factor. Where else can we go with this? So 15, that's also divisible by 3. 30 is also divisible by 6. So let me put the 6 somewhere. That's got to be connected to the 3. So maybe back here. It's almost a cube forming here. So 6, and then it's sort of connected to the 3. 6 also divisible by 2, so there's sort of a 2 down here. Okay. And then we've got 1 down here. I think this is going to be the divisibility lattice for 30. So it's like a cube, basically. But yeah, you can basically picture the entire integers as one big, extremely convoluted divisibility lattice. I mean, you can even see this picture is even you can see this the part with the 6 there. So I can actually extend this way to get the 12 and the 4, and I guess this one's living over here too. The 8. Of course, it's not really all a 3D picture because there are other primes too, right? There's a 7 jumping off here somewhere. You get the idea. This gets very, very complicated. But that's sort of what this relation looks like. Okay, let's go to another piece of paper. So, Well, we already understand divisibility pretty well. Like we've been working with divisibility all our lives. So, for example, even and odd numbers. What does an even number mean? So n is even. Let's write that in terms of our divisibility symbol. So what does it mean to be even? It means that 2 divides n, right, in that order. Which is saying, n is 2 times some integer. 2 times c. Okay? And then odd, so n is odd. The way to think about odd is n has the form 2c plus 1, let's say. So c here, very important, it's an integer. Okay. What about 2c plus 2? Well, that would be even again, right? 2c plus 2, you can just factor out a 2. And you get 2 times an integer, so that's an even number. This is how you should think about even and odd numbers. So you can use this to prove many facts about, for example, why is an even number plus an even number equal to an even number? Why is that true? Well, let's take an even number, 2c, take another even number, 2d. What is their sum? It is 2c plus d, which is even. It's 2 times an integer, right? C and D are integers. You can also try to prove that an odd number plus an odd number is actually an even number. Just using this instead. Can multiply even numbers. So what about an even times an even? Well, we get 2c times 2d. That is going to be 4cd. So not only is that even, it's a multiple of 4. So we just proved that a product of any 2 even numbers is a multiple of 4. It's 4 times some integer. Let's do odd times odd. This one's actually rather interesting. So we'll take 2c plus 1, that's an odd number, times a different odd number, possibly. Not necessarily the same one. What's that going to equal? It's going to be 4cd plus, I've got these cross terms, 2c plus 2d plus 1. Okay. What do we get here? So we've got a 4, a 2, and a 2. Let's take a 2 out. So we've got 2cd plus c plus d plus 1. Right? That looks like an odd number to me. Right? We have 2 times an integer plus 1. So this is odd. Right? That's exactly the form of an odd number. Okay. We can do something really cool here. So here's something that's harder to prove. Let's prove that an odd square, so a square number that's odd, is actually, not only is it odd, we're going to say it's 1 more than a multiple of 8. How can we figure this out? I mean, you might have even observed this. So if you're ever playing around with squares. All right, write out the first few. Look at the odd ones. That's 1 more than 8. 25 is 1 more than 24, which is a multiple of 8. 49 is 1 more than 48. That's a multiple of 8. The odd ones always seem to be 1 more than a multiple of 8. Let's see if we can prove that. Well, first of all, I know that an odd square is going to have to come from squaring an odd number. Okay, so that's an important observation. I know that because if I had an even number that I squared, that's going to be an even number. Okay, we proved that here. Okay, so what does that mean? It means that an odd square is of this form. Let's say 2k plus 1 squared. Okay, that's an odd square right there. Okay, it's a square of some odd number. That's the only way to get an odd square. Let's actually multiply that out. So it's 2k plus 1 times 2k plus 1. We get 4k squared plus 2k plus another 2k. That's 4k plus 1. And I'm seeing right away that this looks like it's 1 more than a multiple of 4 at least. So that's partial progress. Okay. Why is it 1 more than a multiple of 8? Well, maybe we need to look further here. So we have a k squared plus k. I think I can pull out a k there. Let's do that. And now we have 4 times k plus 1. Okay? K and k plus 1 are 2 consecutive numbers. That means one of them has to be even. Right? I don't know which one. I can't tell you which one, but one of these has to be even. One of them has to be even. Okay. So this is actually 4 times 2 times something, right? Times something, some integer, plus 1. So that's 8 times an integer plus 1. So we did it. We proved that any odd square is 1 more than a multiple of 8. Okay. So rather interesting property of squares. Let's do another example like this. So here's another example. Let's prove that this expression 4 to the power n minus 1 is always divisible by 3 for any positive integer n. I guess I could include 0 also, because if we have 0 for n, we get 1 minus 1, which is 0, and 0 is always divisible by 3. 3 divides 0, right? That's how you'd say it. Anything divides 0. 0 is divisible by every integer. Okay, how can we do this one? We're actually going to learn a technique later in this course that will essentially allow us to do this one instantly. That's modular arithmetic. So once we get a bit comfortable with modular arithmetic, that's going to be a really powerful tool. And we can do this problem essentially instantly. Let's try to do it without modular arithmetic. So I want to prove this is true for any positive integer n. I want to prove something is true for all the positive integers. It kind of sounds like I can use induction maybe. So maybe that's can be our idea. Let's use induction. Okay, so how's this going to work? Well, let's try n equals 1. We get 4 minus 1, that is 3. True for n equals 1. Yeah, because 4 minus 1 equals 3, which is divisible by 3. Okay, what next? We want to suppose now that for n minus 1 is divisible by 3. Let's use our notation. 3 divides for the n minus 1. And then we want to show that, what do we want to show with induction? We want to show that we can get 3 dividing the next one in the sequence, right? So we want to show that 3 divides for n plus 1 minus 1, right? But this is what we're allowed to assume. We're not assuming this. We want to show that this is true. So let's start with this. What exactly does that mean? It means that 4n minus 1 equals 3 times something, right? 3c, let's say. Okay. We want to show this, so let's start with this number 4 to the n plus 1 minus 1 and see if we can maybe get this to appear over here, 4 to the n minus 1. Okay. Here's one thing I can do. I can factor out a 4 from this. I can rewrite this exponential as 4 times 4 to the n minus 1. But unfortunately, the parentheses aren't like this around the 4 to the n minus 1, so I don't have exactly this. But that's okay. I can write 4 to the n equals 3c plus 1. So I can replace, this is what I'm assuming to be true over here. So I can replace the 4 to the n with 3c plus 1, right? C is some integer. What do we get now? So we've got 12c plus 4 minus 1, that's 3. And I think we've done it, right? This is 3 times, factor out the 3, that's going to be a really typical idea. We see a common factor, factor it out, and then this thing is an integer because c is an integer. So we proved that this is divisible by 3. In other words, 3 divides this. So we're done. Okay, so next we're going to add one more layer of complexity and consider divisibility of multiple integers simultaneously at the same time. So it's a new concept. So we'll define, I should add an extremely important concept in what's about to follow. So we'll define the greatest common divisor. The greatest common divisor. Denoted GCD of a and b, so a and b are 2 integers, to be exactly what you think, right? To be the largest positive integer, d, such that d simultaneously divides a and b. So d divides a and d divides b. Okay. So note one thing here that we didn't have before. We're really insisting that the GCD is going to be positive because otherwise there's some ambiguity. It might be positive, it might be negative. So we'll say that we want it to be a positive integer. Let's do some examples. So how about the GCD of 4 and 10? All right. Well, we want the largest d that divides both 4 and 10. So 4, the divisors are 1, 2, and 4. 10 divisors are 1, 2, and 5. So I think 2 is going to be our GCD. Let's do an example with 0. So 0 and 5. These are always tricky to think about. What is the largest number that divides both 0 and 5? Well, what divides 0? Something divides 0. So d divides 0 means, let's just remind ourselves again. So that means that there's some c such that dc equals 0. Okay. Sounds like d can be pretty much anything, right? So anything divides 0, right? Well, why can d be anything? Because I can pick my c to be 0, right? All I need is there exists an integer c such that dc equals 0. So what this means is I just take the largest divisor of the 5, which is 5, right? 5 divides 5 and 0. So that's the GCD. Let's do maybe a more complicated example, just to show you maybe some techniques for actually doing this calculation. So I can actually think of 3 techniques for doing this. The first is just to write out all the divisors of 48 and 84, kind of like I was doing here. Right, 10 is 1, 2, and 5, and 10, I suppose. And then just pick the largest one on both lists. I don't really want to do that with these numbers because it feels like these have a ton of divisors. Another way is to write the prime factorizations of each of these numbers. So 48 is 2 times, well, it's 16 times 3. So 2 to the 4 times 3, that's 48. What's 84? 84, let's see, it's 12 times 7. I've got a 7 in there and a 12. A 12 is 2 squared times 3. Notice I'm using unique factorization here. So we'll talk more about this later because it's actually quite a subtle concept. But we're using the fact that every number factors uniquely into primes. And so because it's unique, I can sort of pick out the greatest common divisor by just taking the largest power of 3. So I see a 3 in both of these. I'll definitely take that. I can't take the 7 because there's no 7 here. And I see a 2 squared. Here I have a 2 squared times some more 2's, but I'll just take the 2 squared from both of them. Okay. So if I take a higher power of 2, then that won't divide 84 anymore. So it looks like my GCD is 2 squared times 3, which is 12. Okay, so that's a quick way to do it. In the next lecture, I'm going to show you a third way to do this, which turns out has an enormous significance to number theory. It's going to be the Euclidean algorithm. But I'll be the next lecture. Should we do one more just really weird example? How about the GCD of 0 and 0? So remember we talked about how anything divides 0? So it seems like this can be any number. So maybe it's undefined. A lot of people do just define this to be 0 because it turns out it works better that way for a lot of other things. But yeah, I'll just point out, so I've seen books do it both ways. So it's either undefined or 0. I'll put the question marks there just to indicate not everyone agrees about that. Okay, what's next? So, very important concept. So we say A and B integers are coprime. Not prime, but coprime. Prime together if their GCD equals 1. Oh, actually, so GCD AB equals 1. I was about to just write that symbol without the GCD, and I should point out actually that this, just A comma B in the parentheses, this is a shorthand notation for GCD. Shorthand for GCD of A and B. I'm going to try to avoid using that for obvious reasons, just because this is used for a million different things in math. It could be an ordered pair, right? So you have to kind of go by the context. But yeah, often if you see this in a book, it could mean GCD if it's a number theory book. Okay, so they're coprime if they're equal to 1. This does not mean that A or B have to be prime. They might, maybe neither of them are prime, right? So for example, GCD of 4 and 15. Well, 4 has factors 1, 2, and 4. None of those are factors of 15 except for 1. So 1 is actually going to be our greatest common divisor. So 4 and 15 are coprime. They're coprime. Also, relatively prime is another term for that. Yeah, they're coprime even though neither 4 and 15 are prime. So it's a different concept than being prime. Let's do an example with coprime. So let's prove that the GCD of n and n plus 1 is always going to be 1. So any 2 consecutive numbers are coprime. The logic there is that, divisors of one of these can't be divisors of the next one unless it's number 1. Because, for example, if n were a multiple of 5 or whatever, then n plus 1 would not be a multiple of 5. It would be 1 more than a multiple of 5. So I think we can trust that this is true. How would we prove it formally? Um, well, what does GCD mean? You kind of just always go back to the definition. So um, we want to show that the largest thing dividing both of these is 1. So let's suppose D divides N, and D, we need a common divisor, so I'm really using the same letter here. And D divides N plus 1. Okay. One way that often you can do this is you can assume that D is larger than 1 and try to get a contradiction. Often a slightly more elegant way is to just assume that D divides N, assume D divides this, and then what do we want to show at the end? We wanted to show that D is a number 1, right? So it's not really a contradiction, it's just showing that these two things imply D has to be the number 1. So our goal, our goal is to show this arbitrary D is number 1. Okay. Okay, how do we do that? Well, when you're in doubt, just go straight back to the definition. So what does it mean for D to divide N? This means that D times some number C equals N. What does it mean for D to divide N plus 1? It means that D times some number, is K, I guess, is N plus 1. Okay, I'm not using the same C there. It could be a different one. Now I see N in both of these, so maybe I'll replace this N with DC. Okay, so I'll replace that N with DC. And then I can combine these like terms. So I get dk minus dc equals 1. And factor out the d. We've seen this idea many times so far in this lecture. And let's stare at this for a second. We've got d, which is a integer. Okay. And k and c are integers. We have a product of integers equaling 1. Okay, that's awfully strange. So what does that actually mean? Well, it means d is it has to be 1. Right? We can also assume d. Yeah, d is a positive integer. Okay. All right, so we're done. So the only thing dividing both n and n plus 1 is the number 1. Okay, that's the only positive integer, at least. There's also negative 1. Okay, so we proved it. Remember, GCD is always defined to be positive. Okay, so I think I want to do one more problem just to give you a taste of solving Diophantine equations, because we already have some tools that we can use to solve some Diophantine equations. This is what we're going to be doing sort of toward the end of this course, but just can't help but introduce one of them. So let's look at a Diophantine equation. I'll remind you what that means. Diophantine equation. Yeah. So does the equation 15x squared plus 4 equals 9y squared have any integer solutions? That's what it means to be a Diophantine equation. Diophantine equation, we're looking for specifically integer solutions. Okay, where x and y are both integer coordinates. So looking for x comma y. So x and y are both integers. Yeah, write that out. Solutions. Okay, so you can try plugging in some numbers, see if you can find any solutions. That's often one good way to start. often what you can do is you can use divisibility to rule out either certain solutions or solutions altogether. So in this case, we can actually rule out solutions altogether by using divisibility in a clever way. So first of all, I'll maybe sort of isolate this useful fact. This is a fact that we're going to be using a lot. So the fact is that if I have some integer, d, dividing two different numbers, x and y, then, by the way, I notice I'm not being super careful about like writing down whether something is an integer or not. Basically, everything in this lecture is integers, because if we're talking about things like rational numbers, well, then everything divides everything. I can always find a rational number to divide any other rational number, as long as we stay away from 0. So everything here is integers. Okay, so if d divides two different integers, then d divides their sum. And d divides their difference. So you can probably see why that's true. So, like for example, if well, yeah, let's prove it really quick. So here's the proof. So if d divides x, that means that d times some number c equals x. If d divides y, that means that d times some other number k equals y. If d divides, well, I don't know this, right? I want to show that d divides x plus y. So let's consider x plus y. Okay. So I'm writing down what I know, and then this is the thing I want to prove. I want to prove that d divides their sum. So I'm going to take a look at that sum and try to show that d divides it using what I know. So I'm going to take x plus y, but I'm going to use what I know. So it's dc plus dk. Now I can use the same idea. Pull out the common factor of d. And there we go. We just showed that d divides x plus y because everything here is integers. So we're done. Let's use this useful fact for our Diophantine equation. So let me write this equation down again. And here's how I'm going to do it. So I notice there's a 9 and a 4 and a 15, and 15 and 4 are coprime. 9 and 4 are coprime. 9 and 15, though, those do have some common factors, or one common factor. It's not one. It's these are both divisible by 3, right? 3 divides 15, 3 divides 9. So let's try to exploit that. So I'm going to move this term over. Then I'm going to rewrite 9 as 3 times something. And rewrite 15 as 3 times something. Because probably guessing what I'm going to do next. I'm going to pull out one of those factors of 3. And then we have this. Okay, 4 equals 3 times something. But here's the thing. If we had an integer solution where x and y are both integers, this will be an integer. This will be an integer. What is this telling me? It's telling me that 4 is divisible by 3. So 3 divides 4, which is nonsense, right? It's false. You can't multiply 3 by something to get 4. So therefore, there are no integer solutions to this Diophantine equation. So there are no integer solutions. Very nice. So yeah, we proved that no solutions exist to at least this equation here. And this is often a good idea to look out for when we have a Diophantine equation, to take a look at the coefficients and see if we can say something about divisibility to rule out possible integer solutions. Okay, so let's end it there. Next, we're going to take a look at the Euclidean algorithm.